an old problem.
All right. Can you hear me?
Yes.
Yes, yes.
Okay, and do you see my pointer? No
Yes.
pointer? Ah, you see it. Okay, good. All right. Okay. So thanks very much, Andy, for the invitation. And yeah, so in the second part of this mini lithium fest, I'm going to talk about new physics solutions to the lithium problem. It's new physics, but these are not new solutions. Oops. Now so the stuff I'm going to talk about has by now already some historic value. So sorry, it's nothing hot off the press, but still it's BBN. And so the talk is based on two papers, one in 2010 and one in 2016. One written as a young postdoc with Maxime, and another one as a young faculty. So I guess given that the lithium problem is almost as old as 1665, it's okay to have a conversation about it every 5 years or so. And so this talk will have two parts. The first part will discuss the potential lithium solution due to new sub-GeV scale particles. And when they inject energy through the decay, they can upset the ordinary standard picture of BBN and lead to lithium depleting features. And the second part will be on having relics that are somewhat lighter at the MeV scale, and if they get actually absorbed by nuclei, then this also sets off a lithium depleting chain. And if you're interested sort of in a general review of BBN as a probe for new physics, you can also consult this work here. Okay, so Brian very nicely already prepared the grounds. Let me just very briefly say in a few words that standard BBN is really this remarkable time in the cosmological history where all forces come together basically. So I mean, gravity tells us the expansion rate given its given the ingredients to the universe. The strong reactions determine the nuclear reactions that are involved and that we measure in the lab. The weak interactions determine the balance between neutrons and protons, and then most crucially by that the helium abundance, and then the electromagnetic interactions. Finally, they are responsible to shutting off the light element production just due to their Coulomb repulsion. Due to the Coulomb repulsion, these nuclei, ionized nuclei feel. All right, and so most importantly, today, given the CMB inferred value of the baryon asymmetry, and assuming a boring or non-eventful universe between the time of BBN and CMB, it basically fixes the baryon to photon ratio at the time of BBN, and that so it becomes an input parameter, and overall BBN then becomes a parameter-free theory. So it's a great testing ground for any types of new physics, and so the general concordance of predictions and measured abundances then makes this one of the most important tests in cosmology, the consistency of any new physics. All right, Brian already showed you this picture, just circles were squares, and the reaction network looked a little bit different. I just like this version much better, which was drawn by Mukhanov a long time ago, because it sort of shows the pipe system of how nuclei are formed. So how we go from protons and neutrons to deuterium. We can use background ambient photons to bring it back to protons and neutrons. But then once deuterium builds up, we go into the mass 3 elements. There's also some cross channel here. And finally, everything ends up, all the neutrons end up in helium-4 because it has the highest binding energy of all these elements. And so energetically, it's favored that the neutrons go into helium-4. And then there's a little bit of mass 7 also produced. Lithium-6 is missing here because it comes out with a tiny abundance. So here in the picture again, you see here temperature from left to right. Protons and neutrons, they freeze out. Neutrons decay with a lifetime of 880 seconds. then the deuterium bottleneck is really this little kink here you see in the proton abundance, where light element, where deuterium starts building up. Once deuterium is here, it gives way to helium. Deuterium keeps burning through DT reactions, and then deuterium proton reactions to helium-3 that Brian briefly mentioned, and then it freezes out. And then down here, we have at the baryon observed, at the CMB observed baryon asymmetry, mass 7 comes out in form of beryllium-7. And so this is this freeze-in line here. So it builds up with a sub-Hubbard rate, and then it freezes out. And beryllium-7 at a much later time in the cosmological history, once it receives its first electron, so it's actually the first element to recombine. It's not helium or helium-4, but it's beryllium. So it gets its first electron, and once it gets it, it immediately captures it and transforms itself into lithium-7. So this is why solving the lithium problem, if you want to do it primordially, you have to solve the beryllium-7 problem. Okay, so how can we go beyond the standard BBN picture? Here I show you three general classes of how to do it. I mean, probably perhaps the best known way of altering the standard BBN prediction is through changes in timing. For example, say if you have evolution of Newton's constant, then you would change the Hubble rate. Or if you put more radiation degrees of freedom in the early universe, then you can speed up the Hubble rate, for example, and then change light element abundances. You can do crazy things like having electromagnetically charged heavy relics around that could get captured onto light nuclei, and by that produce a new, completely new reactions that wouldn't be possible in the standard picture. Or you can have some relics that decay into standard model particles, either electromagnetically or hadronically, and they would then set off energetic showers and sort of give rise to non-equilibrium processes and spoil light elements and screw things up badly. All right, let me just very briefly mention these generic possibilities. So for example, if you input additional dark radiation, so you increase the standard model radiation content by, or the usual radiation content by some new light particles, for example, the most important consequence is that the helium abundance goes up because neutrons have less time to decay before they get incorporated into helium-4. And so helium-4 rises. By now, as Brian also mentioned, we have this super precise deuterium determinations to better than 1%, and so now deuterium also becomes a constraint on this extra radiation. So if we do this, what I briefly alluded to before, if we do have this crazy thing of having some electromagnetically charged particles, for example, you can make helium-4x particles, and then instead of sort of a standard reaction where you produce lithium-6 through this photon-emitting radiative capture reaction of helium-4 and deuterium, you could go in a radiationless through a radiationless fusion of lithium-6 with the catalyzer of this X- here, and thereby greatly enhance the lithium-6 content, for example. So here's it's an old paper, but sort of a very drastic modification you can contemplate. Regarding the third class, energy injection, here I want to mention that already standard BBN has a built-in energy injection, just because I mean, there's a mass effect in nuclei. You radiate off the binding energy, and it's about 2 MeV per nucleon. So it's not little, and MeV is sort of the nuclear energy scale. So if you input MeV energies, in principle, you could hope that something would affect the picture that you might not capture in a standard BBN calculation, just because you assume perfect kinetic equilibrium and perfectly thermalized species. But it turns out that at a temperature of 1 billion, this is a completely negligible effect, just the plasma is optically fake to any of these things. The most prominent class in this sort of non-equilibrium BBN scenario that has been historically studied best are the case of long-lived particles X that are sort of on the electroweak scale. For example, take gravitino decaying to standard model and the neutralino and so on. And so these sort of, if you have so much energy that that gets dumped at an individual particle decay into the plasma, you produce all these electromagnetic and hadronic showers. And for example, if you have now energetic neutrons that zip through the plasma, they are, although they have a magnetic moment, they are stopped poorly in the plasma, and so they can stream until they hit another helium-4 nucleus or whatever and split it. And so this generally leads to big departures, and it's also a rather complicated endeavor to capture these departures accurately. But so there's much work that has been put into. The question I want to address here is what happens if you actually dial down this mass of this particle and put it at or below the GeV scale, and we'll see how things change. Okay, just to give you a general overview into the phenomenology of energy injection, one discriminates between these two classes, as I said, electromagnetic and hadronic energy injection, and they are really disjoint almost in their phenomenology, because electromagnetic energy injections are not important until the universe has cooled sufficiently and is about 1 million seconds old. Before that time, sort of all these photons their energy gets dispersed very quickly, and so you need to rely on those few photons that sort of break out I mean, they get dispersed mostly through a plus and minus creation. So you take a photon and the CMB photon, you make it plus and minus, and then you basically have sniffed out that high energy photon. And that reaction only becomes non-efficient at low enough temperatures. So when the CMB or the ambient photon energy is low enough, and then you break out photons from that depleting chain, and then you can start swallowing, for example, helium-4, you make a mass 3 or deuterium. Some of this mass 3 may actually be energetic enough to zip through the plasma and hit another helium to make lithium-6, for example. And this was pointed out long ago that this is an important secondary production of light elements. Now, what happens if we inject hadrons, but we do it sort of softly? Is this a possible lithium solution? And so now for this slide, I want to take you, I hope you can pay attention, because that's the main, that's the crucial thing. So let's, for example, consider some particle that decays into pions. If that's the case, then the pi minus particles, they will, before they decay, they will interact with the most abundant species in the universe, and that is protons. And they can make a charge exchange reaction and give you an extra neutron. Now, what this will do generically, you already know, extra neutrons, they go into helium, it will elevate my helium abundance. But there's another beneficial thing they can do, is if you here are shown the neutrons. So now the dotted line is the standard abundance. And now these the pi minus here, the charge exchange on the protons, and they give you this little extra bump on neutrons here. These extra neutrons, the beryllium-7, it likes those neutrons. So it will capture them right away and turn itself into lithium-7. Now you will say, oh, not much has happened, I'm still with mass 7. But now lithium-7, it has one less charge. And so the burden, or the repulsion against being burned on a proton is accordingly less. So the Coulomb repulsion is reduced. And so now this proton burning reaction transfers it back, the mass 7 back into two alpha particles. And thereby overall in this chain, you can see it here, you have depleted beryllium-7. And so you don't need that many extra neutrons. You need it basically at the level of 10⁻⁶ or 10⁻⁵. measured relative to baryons at the critical time, which is about 1,000 seconds or so. All right, so this is the picture then. So here I show you some exotic particle X with the lifetime between 100 and 10 to the 5 seconds, and you give it some initial abundance and you let it decay into pions. And so these bands here then show you the bands where you actually solve the lithium problem. And what I told you before, so if the lifetime becomes short, then you start being faced by elevated helium abundances because you do this, you create extra neutrons. The problem, however, with this scenario is that these extra neutrons here, most of them, they are not captured by beryllium-7, but most of them, they are captured by the protons. And so you will also be faced with additional deuterium abundance. And so this is shown here by the dotted lines. And so back in 2010, it was okay to have deuterium abundance of 4 times 10 to the minus 5. But today, with these sub-percent precision determinations of the deuterium abundance, this is all ruled out now. Okay, so upshot is here we identified the potential promising chain of solving the lithium problem, but today now this has been excluded just because deuterium is so precisely measured. So no lithium solution here. Yeah, let me skip over this. So in fact, if you really want to capture this accurately, you have to account for delta resonances in the proton-neutron conversion, but overall the picture doesn't change here. Yeah, you can also study, if you dial up the mass of this progenitor, you would also inject kaons, and then it becomes really crazy because then you have S-quark exchange reactions, you produce hyperons, they decay, or the kaon could be captured by helium, produce lambdas and so on and so forth. So it becomes arbitrarily complicated and you can spend an arbitrary amount of time. And back in 2010, I did that. And so this is the results we got. But again, here, you won't change the overall picture. You will still have high deuterium abundances. There's one fine-tuned solution though. It doesn't need to be hadrons. You can also have X decaying into muons, for example, because they will source neutrinos. Now, what do neutrinos do? They can also charge exchange on a proton and make a neutron. So it can also give you an extra neutron. And again, you can solve the lithium problem. Of course, now the initial abundance of these X particles must be much higher because you are relying on a weak process to make those extra neutrons. But what is beneficial for this is sort of you inject these neutrinos and they basically free stream. And so the activity these particles have, or they stay reactive for many Hubble times until they free stream below the Q value of the reaction. And what fine-tuning means here, again, you would have a high deuterium abundance, but then if these X decay late enough, then you can use electromagnetic energy injection of these these decays to deplete the deuterium abundance again. So this is shown here. You produce extra neutrons, these X decay, but then they also lead to electromagnetic energy injection, and that sort of puts back deuterium onto the line where it came from, while at the same time here solving mass 7 problem. Not pretty, highly tuned, but in principle a lithium solution. All right, to summarize here, the moral of that story was really that today, when you want to do anything to change the standard picture of BBN, you will be faced with the precision determinations of deuterium. And in particular, for solving lithium problem, this puts a serious constraint, although fine-tuning is possible, as I've shown you. However, now I would like to argue that there is yet another way in this picture how to alter the standard BBN predictions. namely if we absorb a particle. So we don't let it decay, but we let it being absorbed by the light nuclei. Okay, so what we need is obviously some bosonic state X, because it wants to be absorbed, that lives at least long enough so that these light elements are already there when this particle gets absorbed. So 100 seconds or longer. So that's when the light elements, in particular beryllium, builds up. It needs to couple to the nucleus, so it should couple to quarks. And it should have a mass or energy that is at the level of the binding energies of the light elements. And so in fact, the lightest or the most shallow bound light element is beryllium 7, and it has a binding energy of 1.6 MeV. So that's the most lightly bound nucleus. After that comes deuterium with 2.2 MeV binding energy. And so if this X particle gets absorbed, and say it's heavier than or more energetic than 2.2 MeV, it will dissolve this nucleus into its original constituents. In order for making this efficiently enough, so to catch up with the Hubble rate, basically this has to be a relatively abundant state relative to baryons. Okay, so now the whole play here is that I showed you before, if we have extra neutrons, we have this nice lithium depleting reaction. But we were faced with the problem that extra neutrons are all gobbled up by protons and make high deuterium. But if we have these absorptions, then we can actually dig these neutrons out from their nuclear graves. So these are zombie neutrons, if you want. We just borrow them for a little while. So we split deuterium by absorbing these X particles. Then you get some extra neutrons, and these neutrons, the capture reaction back on protons is actually very efficient. So all these borrowed neutrons go back to where they came from. They all go back to deuterium, except a few of them which actually make this lithium depleting chain. And so by that, you have now identified a process that keeps all other light elements unchanged, but just differentially depletes beryllium 7. And this is, I think, a very nice observation. And here I show you the plots in parameter space where we plot the initial abundance of these particles times the cross section of being absorption of beryllium versus the relative importance of deuterium versus beryllium for two different lifetimes here. If these X particles would have an infinite lifetime, then here you can solve lithium either through directly just split up the mass 7 or go through the borrowed neutron mechanism. But if these X particles live long enough, then at some point you will really, the neutrons come back to deuterium, but they will be again split by the X particles that are still around. And so you will be faced with high deuterium abundances. And so you're back to the original case, basically. But if the lifetime is 1,000 seconds, then there's no problem with that. And indeed, you get a very nice solution here. Sorry. So essentially, what you have to do in this blue band, the condition is just that the absorption rate is comparable to the Hubble rate. And then because beryllium 7 is a freezing production, so it's sub-Hubble, it's not going to come back. So once you deplete it, it's gone. And so if you take, for example, a 5 MeV particle, and you say you don't want to have it more than 1% of the energy density of radiation of that in photons, then it puts you at this value of the cross-section, of the absorption cross-section, in that ballpark. So it's much smaller than the cross-section of a photon that would get absorbed on a nucleus, but it's much larger than weak interaction cross-sections. But however, the lifetimes need to be comparable to that of beta decay. So it needs to live at least 1,000 seconds or so. And so that tells us that this X particle, it would need to have a very small coupling to electrons or to photons and neutrinos just to stabilize it. And so basically leptophobic models are of interest in this for this lithium solution. And so what could it be, this X particle? It can't be a dark photon, as I just mentioned, because to stabilize the dark photon, you would need such minute kinetic mixing angles that it basically doesn't interact at all anymore at BBN times. Could it be a different vector? Yes, it could be perhaps a baryonic vector. So if you gauge baryon number, so it would directly couple to nucleons. However, you could sort of put in a quark loop, and then this thing again couples to E plus E minus. And so generally there's some radiatively generated mixing with a normal photon. And so perhaps this works, but it's a model that would need to be tuned in the radiative processes to have it long lived enough and still have large couplings. It could be, we haven't studied this in detail, but it could be the Higgs that breaks the U1B, because it checks off at least on being long lived, and it checks off on being directly coupled here through a loop of being coupled to nucleons, so it can be absorbed. In the end, the model we chose in the paper was to take an axion, or an axion-like particle that couples to down quarks, and so at low energy you have this general description here. The particle, this ALP now decays to photons through the pion mixing, and this is sort of the dimensional estimate that you would get for this for the axion photon mixing for the axion pion mixing with an axion mass that is much lighter than the pion mass. And so you see, if you want to have a decay time of about 100 seconds and the mass that is on the MeV Pohlbark, that puts you at the scale of this operator at the 1 TeV level. So this is basically, this is a low scale axion. It will be trapped inside stars. Why down quarks here? Because we need to evade some flavor constraints like K to pi invisible. So it shouldn't couple really to up quarks. In principle, it's possible. So that's fine. And yeah. So and then there are two generic possibilities. How you need to source these axion-like particles now. Either they could be relics, and of course you need to arrange a model to give them a relic abundance that's okay. So there need to be new particles there. Or the other possibility is you have some progenitor state that of course has its own model, but the progenitor state it decays into this axion and injects them. So here now this is the scenario where this A particle, it can be almost massless, but it is energetic and energetic enough so that it splits the nuclei. When it gets absorbed, it splits the nuclei. So the picture here is that at some point you inject these particles with a particular energy here, which is half the mass of the progenitor, and now they sit through the plasma. And once BBN has created the light elements, then it can in principle be absorbed. But at some point it redshifts enough so that it won't be able to be absorbed onto deuterium anymore, or split deuterium. And then at some point it becomes even redshifted enough that it can't split beryllium anymore. And then at that point it becomes sort of an inert particle. But as in the case of the neutrinos that I mentioned before, here you get sort of the phase space of this, the phase space distribution of the particles it's basically like a pileup. You inject fresh particles, and so they all redshift, and so you get a pileup of low energetic particles with a certain threshold where you can absorb these guys. And then as to the cross section of absorption, that can actually be related to the absorption absorption of a photon through some quantum mechanical considerations. And so basically, one has a reasonable idea what is the cross section for the absorption here. And that's here now shown you for, we take an exemplary abundance of these guys, some mass of the progenitor, and lifetime, and this Paget-Quinn scale here. And now you see that's where you have the solution. Of course, these types of physics is tested, for example, at the intensity frontier. So when you have a proton beam on a fixed target, you not only produce a whole lot of pions and kaons, or light mesons, but also now these X particles, and they could be absorbed in a neutrino detector like a mini boon or LSND, and then it gives you, it looks like an electron scattering basically. And so back at the time when we wrote the paper, we made a very simplistic estimate showing where is this direct constraint, and LSND here gave the most stringent constraint here, excluding this lower part of the barometer region. And this is something now after 5 years, I think I want to return to this subject here with the student, Raylin Kuo here with me in Vienna, and we have plans to revisit these lithium solutions and really sort of put an intensity frontier test to this solution. All right, that brings me to my end. So, well, as we heard in the past hour, that BBN provides a non-trivial cosmological test to any new physics, really, that has some particle content present at the 1 second after the Big Bang. There's one quantitative persistent problem, and that's lithium seems to be high by a factor of a few. For many years, the role of stars is perhaps very important, but very difficult to understand. I've shown you that if you have soft energy injections, you can set off a lithium depleting chain by creating extra neutrons. But if you do extra neutrons, then you have this trouble with deuterium. But if you borrow the neutrons, when you dig them out of their nuclear graves for a little while, then you keep deuterium in place, and you have honest to God lithium solution, and something that is actually searchable in present day experiments. Thank you very much.
Thank you, Josef. It was very nice review about the situation of the new physics in lithium trouble. So, any questions?
I have a question, Josef. It's a very naive one. If you can go back to slide 4. There is something I missed, I guess. Because you were mentioning in the context of the standard BBN, the fact that...
Slide 4 is which one?
4.
I don't have slide numbers on my... Oh,
no,
actually, wait, I do. I just... some have, I think.
It's the one before.
Okay.
Yeah, the next one. Okay, sorry,
okay.
The next one.
Oops. Okay.
Yeah, here. I mean, you mentioned in the lower right corner of the figure that the beryllium-7 eventually goes to lithium-7.
Yes.
Now, beryllium-7 is much more abundant than the lithium. So I wonder why there is no indication of the lithium-7 growing to the rate of to the density of beryllium-7 after this process.
No, so at the I'm not sure if I understood the question correctly, but the lithium at CMB time, it's all lithium-7. So what happens is it takes a long time before beryllium-7 can finally get an electron in its shell, just because of the overabundance of energetic photons in the CMB. But once it gets it, it instantly converts itself to lithium-7. And that happens sort of before the main stage of recombination.
But the time scale here is like 10 to the 6 seconds, right?
Yeah, this error here doesn't, so it goes down later.
Oh, I see. So this is after.
Yeah.
Okay.
Yes, so this is after. I mean, CMB is 10 to the 13 seconds, so I think at 10 to the 12 or so.
So, more questions?
Yeah, yes, I have a naive question. If axions can change the lithium abundance, won't that set an upper bound on how much dark matter could be axions in the first place?
Yeah, this is not a dark matter solution to the lithium problem.
No, but it tells you that you can't have a lot of axions to be dark matter because you get too much lithium.
No, so these axions are really completely disjoint. I mean, it's they disappear, they decay to 2 photons, but it's not going to do any harm, and because decays into photons would need to have MeV scale energies per baryon in order to make an observable effect, and so this stuff just disappears basically, and it's not gonna. It's not related a priori to dark matter. It would be nice to have a dark matter lithium solution, but ones I presented aren't of that type.
And if I can ask a separate question, you said that there's a candidate mechanism for changing the timing by having G vary in the early universe. How much do you need it to vary, and how much is it? What are the numbers that you will need?
I don't know off the top of my head, so this is all probes my long-term memory.
Okay.
But I think the papers, the people you want to consult is probably Victor Flambaum and collaborators. They have maybe 10 years ago, or I don't know, papers on that. So it's definitely, it's probably, it's a difficult subject. You know, if you start varying fundamental parameters, you start changing many things, and to capture these things accurately, you know, you change positions of resonances. You have exponential dependencies, like, I mean, the deuterium binding energy, of course, the neutron to proton ratio is exponentially sensitive, but there's many things to consider then. So it's perhaps not a super easy answer, but you should just go and look at those papers.
So, more questions? Maybe last one. So, I can't see any. So then I should thank you, Josef and Brian. It was very nice to refresh our memory about primordial lithium and this big trouble. Okay.
Thanks very much.
Okay.
Thank you.